Right, so welcome to Scuffed Data Structures and Algorithm Tutorials number 2. We'll be going over hash tables. So I highly recommend you actually just go watch some videos on YouTube or just do a bit of research on the internet about hash tables in general and how they function before you look at this, so you can have a conceptual understanding of what's going on. I think it would help quite a bit. Obviously I'll do my best anyways, but yeah, please try to do that first. So let's just get straight into it. We'll need this standard lib, and I think we'll need string as well. Yeah, all of you sort of have anyways. Get main out of the way. Okie dokie. I think we're just about ready to get into the meat of things. So. Node, you're already familiar with this, aren't you? I think so, from our last linked list tutorial, but the node structure here is going to be slightly different, so it'll be char star key, right? It's a string and integer value, so key value pair, and then obviously this next bit you're already familiar with. So hopefully you can understand what's going on here already. And then the hash table structure itself is just typed of table, okay, and all it is, it's node star bucket, and let's just use table size. Yeah, makes sense to me. So it's an array of pointers, right? That's all a hash table is, by the way. It's just an array of pointers, and we'll define table size for now. Just want something really small. So let me try to draw this. Maybe it'll help a little bit. I don't know. So it's just an array, right? And arrays have elements inside of them, and each element here is just going to be a pointer to a node structure. Okay. Now obviously the first thing we have to do is initialize the hash table. Right now it's uninitialized, so we'll need a function for that as well. Okay, so what we'll do is we'll say void init hash, just init table, a little bit better. We're going to need a pointer, so hash table, pointer to the table, and all we're going to do is iterate over the entire array. So integer I equals 0, I is less than table size, oops, I plus plus. Can't seem to type for some reason. And all we're going to say here is table dot bucket. I don't know why they call it a bucket, to be honest with you. Well, guess it'll be one of those great mysteries. Is equal to null, right? So every single element, we'll set it equal to null. So after this hash table is initialized, it'll look something like this: null, 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 and this will go on 10 times, right? And this is going to be our hash table structure. So the next thing we're going to have to implement is an insert function. So we'll say void insert. What do we need? Hash table. Don't need a table. And we're going to need the key, right? And we're going to need the value. Yeah, seems about right to me. And so the first thing you have to do is hash the key, right? So we'll use an unsigned integer index. Hash the key. Great. We don't want negative values here, so let's just get that out of the way. Unsigned integer hash, and it just takes in the key, so constant key. Right then. And so what is a hash function? Essentially it's just going to take your key, right, and perform some fancy number theory, and it's going to return an index, right? And so the index is going to be where you're going to store that node, essentially. Okay, where in the hash table you're going to store that node. Alright, so I don't remember what this particular hash function was called, and feel free to use your own hash function if you'd like. And really and truly, the only benchmark you're checking for when it comes to how good your hash function is going to be the number of collisions you have in your table, and I'll try to explain what that means in a bit. So we'll just say unsigned integer hash is equal to 5381. I don't quite recall if this was the exact number. It's been quite some time, but it's a number close to this. It's some special number that some dude came up with. I don't remember what his name was either, but the hash function is named after him, HW something, I don't know, and I won't try to remember either. But okay, I think as long as you get the idea, it should be fine. Then we'll say for, and we'll iterate over the string, right? Integer I equals 0, and as long as key I not equal to, so long as we don't encounter the null terminator, just keep incrementing I, and that will take us over the entire string. And we'll say hash is equal to the original function definition. I remember it was 33 times hash plus key of I. Obviously you can actually just optimize this, so you can say hash plus hash, right? You can use the bitwise operator like this, and it'll be analogous to multiplying by 33. And let me try to explain very quickly why this is the case. So if you had 1, 2, 4, 8, 16, and 32, right? Suppose that this was the binary number that you started with, 0, 0, 1, right? Suppose you started with the number 1. If you perform a left shift by 5, what's going to happen is going to go 1, 2, 3, 4, 5, it'll land here, and you'll end up with this new binary number, which is, if you look carefully, the number 32. So a left shift by 5 is the same thing as multiplying by 32. Okay, and then we just add back hash again, so 32 plus hash 33, you're multiplying by 33. And why are we using these bitwise operators? Well, actually these shifting operators are so fast, right? Computationally efficient. If you've ever built a CPU or done any studying in computer architecture, you'll know that typically these execute in like 1 clock cycle, so it's really optimized code you're writing here, which is obviously important for something like a hash table, right? But hopefully that was clear. And then obviously you'd like to normalize, so you'll just return the hash and table size, modulus table size, so it'll wrap into the table size. So no matter what value you end up, this hash ends up generating, it's going to wrap itself to your index, so it won't overflow outside of your table. Okay, I think we should test that this works, so we'll just go printf %d, and we'll just print the index here. And I think we need to do a bit of work here too, so we'll say hash table, and we have to initialize our hash table. Was it init table? Yeah. And memory address of table. And then we'll just call insert table, and we'll just say apple for now. We'll give it a key, say 5. Right, and let's see. Great, it's printed 1. So let me try something else. Let me try Najdorf. Favorite chess opening. 1. Whoa, it actually, now I'm worried. I'm worried about this 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 hash function. So that actually brings me to a pretty neat point. So already, right, you can see we have what's called a collision, right? Because we have 2 separate keys, but they both return the same index 1. So what are you gonna do, right? You don't want to overwrite the information that's going to be stored here, and that's where the linked list is used to do collision resolution, right? So it'll look something like this, right? And it was at position 1 here, and so what we'll do instead is that we'll add that node to the linked list, to the head of the linked list, And it'll keep growing like this. Every single time there's a collision, the linked list will keep growing. So you don't have to lose your information. Obviously, you want as little collision as possible. I just did not expect Nydorf would give a collision with Apple. Who would expect that? Okay, great. So it seems as though the hash function, well, actually, probability would dictate that it's quite likely because our hash table is already so small, right? It's only 10. So okay, it's not that big of a surprise, but okay. And so, okay, yeah. Hash function works fine. So the next thing we have to do is create the node. So we'll say node star, new node, create node. I think it's fine if we just wrote a function to do this, and we'll give it the key, we'll give it the value. And let's do the create node function here. So return type will be node star. Create node, not create graph. And okay. This one needs the key and the value. And node star new node. I think this should be fairly stock standard by now. Should be familiar with this from the last tutorial. Size of node. Great. And then new node dot value equals value. New node dot key is equal to, and we're going to use the string duplicate function from the string library. If you're not familiar with this, what it's going to do is it'll take a string, right? We'll give it the key. It's going to duplicate that string, and it's going to return a pointer to the duplicated string. And it's perfect because our key is actually expecting a pointer if you look at the definition all the way at the top. And new node dot next, and we can just set this to null, right? Don't see the harm anyways. And return new node. Don't forget your return type. They should be fine. Let me just run this. Yeah, okay. Alright, so we've got our new node created now. It's just a matter of inserting that node. And let's see. Yeah, I don't think we should create this node right away at the top. I think it's a bit more efficient to do this instead. So we'll say node star current. And we'll say table bucket, right? Index. And so it's going to check whatever index was returned here, right? And it's going to throw that value into this pointer current. So now we have access to the head of that linked list, right? So the hash table is just an array of linked lists. You can think of it that way. So we have access to that particular node. And we can traverse the node, right? So we can say while current is not equal to null, traverse the node, if there's anything to traverse at all, right? And what should I do here? I think it's quite important to consider as well. So we'll say if string compare, right? And why are we doing, okay, I'll just type the code and I'll explain. Current dot key, and then key. So what string compare is going to do is it's going to check these two strings, right? And if they're the same thing, it's going to return 0, right? So we'll say if it does find a match, right? If this key and this key is the same thing, it'll return 0. And the reason why I'm doing this is because I'm worried that if I put in apple, right, for instance, and then I insert apple again, right, it's probably going to give me a duplicate node, and I don't want a duplicate node inside of my hash table. And so if I do detect a duplicate node, I want to just update the value, right? So this bit of modification here will allow me to update values as well with the insert. Instead of inserting a duplicate node, I think that's important. So we'll say current dot value is equal to value. And we'll break out. Great. So I just wanted to take care of that. Bit of fringe case there. And is there something else? Let me think. So while current is not equal to null, that implies that there's a node there, right? So we'll have to say table dot bucket, right? Index. This is essentially how we grab the head of the linked list, right? It's equal to new node, pretty much, right? Well, we didn't define the new node as yet. It's all the way at the bottom here. So I can go ahead and cut this and paste it here. I think there's a bit of consideration that I have to do here though. So table.bucket index is equal to new node. If it does, no, I don't think so. I think let's just get rid of this. The only important thing to do is to first check that there isn't a duplicate. So that's the entire function. So if you didn't find a duplicate, then just go ahead and insert it to the head. So table.bucket index is equal to new node, and well, actually new node dot next should be equal to the table bucket index. So table dot bucket index. Yeah, this makes sense to me. Seems pretty straightforward as well, right? So all that's happening here is, oops, let me scroll down. All that's happening, right, is that we've got this linked list here, and I'll just separate it like this. And each one of this is going to represent like a bucket, right, inside of the array. And so let's say this is the head of the linked list here. And let's say it was pointing to null, right? But let's say that we already had a value we inserted here, like apple, right? And then we inserted Najdorf. Remember, when we inserted Najdorf, it also returned the same position, or the same index. And so what we're going to do is that we're going to bring the new node in. We're going to create the new node, right? So the first thing that the function is going to check for is a duplicate, right? It's going to go through the entire linked list, and it's going to check for a duplicate. If it does find a duplicate, it'll update the value, and it'll break out of the function. However, if it doesn't find a duplicate, what we want to do is point this new node to what the old head was, right? So essentially we're inserting at the head. That's what we're doing. So that's what we're doing. New node.next is equal to table.bucket index, right? So we're pointing this to the old head, and then we're updating the old head to be what the new node is. Okay? I hope that makes sense. Alright. So I think this should work handy dandy, but I guess we'll find out, won't we? First of all, let me just compile and ensure that we don't have any issues. We don't. And obviously I have no way of actually testing this, so I have to write a print table function. So print table, I think all we need is the table, and that should be fine. Now, I'm not sure how I want to go about doing this. Okay, well, what's clear for sure is that we're dealing with an array here, so we need to traverse the entire array, obviously. So this much is clear. I is less than table size I++, right? Seems straightforward. From there, I think we can grab the current head based on the current bucket position. So we can say table.bucket I, right? That's gonna grab the current head for us. And while we have the current head, then we can just traverse down the linked list. While current not equal to null, traverse down the linked list. I think so. Yeah, we'll just do printf. And I'm gonna say, what do I want to print out? I'll print the bucket we're in, and then I'll print %s. We'll print the string, and we'll print the value. I hope so. This will be I current dot key current dot value, and then we'll do current is equal to current dot next, and yeah, I think there's one more thing we should consider here is what happens if it's null, right? So we'll just check here. So if current is equal to null, I'll just printf null here. Null, and we'll just do new line like so. Let's see. And there's a problem somewhere. Ah, whoopsie daisy. This is expecting table, hash table start table. Okay, so it didn't compile with any errors. Let's try printing the table now. Print table. Let's see. Where'd that backslash come from? Maybe it just overflowed. Yeah. Okay, great. But why is this in position 7? Why is this oh, I see. Yeah, I'm gonna have to put a new line here then. I really don't want to do this though. I really don't want to do that. Decisions? Whatever, man, it doesn't matter. I don't need a perfect implementation. I just need something that works, right? You guys can figure out your perfect implementation if you like. So 7, 8, 9, and this is 0, obviously. So total of 10 inside here. And let's try implementing. Let's insert rather the. Let's insert Najdorf. Let's insert Apple and Najdorf because we know that gives us a collision, and just by like pure chance. Apple and Najdorf, right? Najdorf gives us a collision. So what's gonna happen is that's gonna insert Apple first, right? And then it's gonna, the collision's gonna happen, and then it's gonna insert Najdorf and the head. So it'll be Najdorf and then Apple. So let's see. Whoa, that's not good. That is very bad. So let's see. Yeah, something's definitely not going our way here. It has to be in the print table too. Yeah, I don't know why this is actually the case here. This is quite weird. Let me comment out this print table here and see what's happening. Yeah, the issues with the insert function itself, not the print. Okay, so let's try to figure out what is going on here. So we hash the index, we get the current index, right? And then we iterate down. So while current is not equal to null, and then we string compare. So if we do find a duplicate, we can update that value and break out. Otherwise, though, we'll just create the new node, and we'll say new node.next is equal to table bucket index. So new node.next. Interesting. Yeah, well, it's null by default. So, however, yeah, well, that makes sense, right? And then the table bucket index would just be the new node. So I don't get why. And it's obviously stuck in some kind of weird loop. Oh. Yeah, it's stuck in the loop because we're not iterating the pointer here. So we'll say current is equal to current.next. Yeah, I think that should be fine. Yep, there we go. So we can come back here now and print your hash table. And we should see it. Yep, there we go. So you can see that Najdorf was placed above Apple, even though it was inserted second. Okay, and we see that it's both in bucket position 1. Yeah, you really got to be careful with these types of implementations, though. You kind of really do have to understand what you're doing, otherwise it's quite literally impossible to debug your code. So hopefully you're picking up at least a few techniques here or there. But really and truly, you shouldn't be looking to memorize the syntax. You should be trying to understand what a hash table is and how you might go about implementing the hash table, okay? So there we go. We can already insert into our hash table. The next thing is to search. So integer search, I think this should work fine. I don't think the search function should be that difficult to implement, but we'll see. Table, hash table, star table, and obviously constant char key. There we go. I think that's all we need actually. So first thing we're going to do is grab the index, so we'll hash the key. This is what makes hash functions really powerful too. Right? You can do really fast lookups. All you have to do is hash the key. Okay, and then we'll say current node star current is equal to table dot bucket the index, right? So we have the head of the linked list, and we can say while current is not equal to null. I think all of this is fairly standard, I think, to follow along with. Shouldn't be that difficult. Now, what I need to do as we're traversing that linked list is essentially check if the strings are equal, right? If there's a match, essentially. So I'll use string compare, so if string compare, and we'll say table, well, current dot key, right? And key. So we're comparing the current key, whichever node we're at, we'll compare its key with the key that we're searching for, and it's equal to 0. So if it finds a match, this is going to return 0. This entire function is going to return 0. So if there's a match, this if statement is going to evaluate to 0 equals 0, right? Which is true. And yeah, then we just want to return, I don't know, current dot value. Yeah, that seems fine to me. And then otherwise, though, if you were not able to find a match, you can return like -1 or something. And so let's try that. Let me just insert another value in here, just to satisfy myself that, you know, something else doesn't magically break. Mario 4. And then I don't know what position Mario is going to be at. So let's see. Oops. Mario is at position 7. Great. So let's search for Mario then. And we'll do it after the print table. So we'll say search the table, and we're searching for Mario. Great. Should return value 7 somewhere. I did not. Oh, well, it didn't because it's just returning the value. We're not printing. Well, I'll print it out like this. So I'll go %d, and then yeah, this should be fine. It should print 7 now. 4. Oh right, sorry. Yeah, it'll print 4 because that's we're returning the value associated with the key. So it'll print 4. That's right. And if we wanted to print apple, let's see if it'll find apple, even though it's, you know, hidden away there. It's not finding apple, which is not good. So let's see, why isn't it finding apple? So hash the key, current is not equal to null, string compare. Because we're not, this is a mistake I made quite a bit as well, I've noticed. This is just something I find very quickly now, I guess. And this should work, right? We weren't iterating, so yeah, it returned 5, right, for apple. And let's try searching for something that isn't there. Let's try apple. It should give us -1. Yeah, -1. Great. Alright, so that's already insert and search, and even the print hash table functions. And there's this one function, I think, left. I have no bloody clue how I'm gonna implement this, but we'll we'll figure it out. So let's say void delete. Yeah, why not, right? And hash table. Oopsie daisy. And we'll need the key. Obviously, the first thing you're gonna do, signed integer index, you just hash the key. Every single time you just hash the key. And we can say node star current is equal to table dot bucket index. So we have the head now of the linked list, and now we just gotta figure out how to delete this. So let's try to see what are some of the fringe cases we might be able to come up with. And this is very similar, I think, to position delete, which we've already implemented before. Suppose this is our linked list, and suppose I wanted to delete, I don't know, this element here, right? So what I can do is I can traverse down the linked list until I find a match with the keys, right? And then I can stop. Now the problem here is that this isn't like with the previous position insert or position delete, where we're passing in as a parameter what the position is, right? So we can stop just prior, because remember, right, if we're going to remove this, we need access essentially to this node here, so we can bypass. Whoops, what's going on here? Come back down, please. So we can bypass like so. So we can do this. So once we free this off, right, we change this to point to whatever this is pointing to next, right? This is gonna essentially not point to this anymore. It's gonna point to the. So if this is, we can call this previous, right? We can call this previous. So previous.next would have to be current.next, if you understand. And then we can free this off essentially, right? I think that makes a lot of sense. And then there's another fringe case I'm thinking about here, which was also the same thing in our, if you remember from our position delete, or even the insert tail and all of the other functions that we implemented in our linked list. What happens, right, if you're trying, there's a fringe case here at the beginning, right? Because there's no node prior to this, right? So you check the fringe case as well, right? So we'll check the fringe case, and obviously if the element we're looking for is already at the start, right? It's the only element in your linked list, or it might already be at the start, then you just point this to the next element here. I'll point over here straight away. So let's try to implement what we just articulated. And so I feel we'll need node star previous equal to null. And then we can say a while, right? Now we traverse down the linked list while current not equal to null. Why does it look so weird? Yeah, and we can say current equals to current dot next, in case I forget to put that in for some weird reason. And then I can check, okay, let's do the fringe case straight away. So if previous is equal to null, should I do this straight away? No. This is not right. What I need to do first is to, as I was articulating, I need to traverse down, right? And every single time I'm traversing, I have to check the key. So I'll do string compare current dot key, and the key, right, is equal to 0. So we're checking now. So if that's true, and that syntax should already be familiar with you, right? So if we've got a hit, right, this is where I think the rubber sort of hits the road. If we've got a hit, then we can say we have to check then, right? We have to check inside of here. So we'll say if previous is equal to null. I hope this works. So if previous is equal to null, it means that we've had a hit, right? But previous didn't update itself as yet. So all we're going to do, so that's the fringe case we were talking about, where it's already at the first element. So we would just have to update the head of the new linked list to be current.next, essentially. So we'll say table dot bucket, yeah, it's called bucket index is equal to current.next, right? Yeah. So we're here, right? And it's gonna update this to be this value here, the next index. It could be null, it could be, you know, a node itself, it doesn't matter. And then we'll free this off later, I guess. And then otherwise I can say, if it's, then we do the other case, the more general case where I was talking about, where the previous would be previous.next would be current.next, right? So previous.next is equal to current.next. And then here at the bottom we can say previous is equal to current, and current is equal to current.next. Hopefully you can see what's going on here. So previous is going to store what the current pointer is at the start, right? And then the pointer is going to iterate. So we always have access to the previous one. And then I think, okay, we don't need this here. Has to be there. And yeah, once we're finished, right? Where do I think I want to return here. Yeah. Yeah, if you finish deleting something, you want to return. Yep, that makes sense to me. And then we can but where are we free? Where am I gonna free that stuff? I don't want to break out straight away because I have to free the, yeah. So I don't want the return statement to be here then. It has to be outside here, no? Let me just go through this. And then we'll figure out where to free the information and all of that. So let's come down back here with our fancy colorings and we'll figure out. So we'll do the first case, right? And we'll make a very small linked list. We'll say the first case is that we want to delete, let's say we want to delete Apple. Let's assume Apple was stored in this node here, right? We want to delete Apple and Apple is stored here. Great. We hash the key Apple, right? And it's going to return the index, right? And we'll grab the current index. It'll set previous to null. And we'll say, well, current is not equal to null. Obviously, current is not equal to null because there's a linked list here, right? Full linked list. And it'll string compare, right? Current, the key, and it'll evaluate to true. And previous is equal to null, right? Because it's set up here. And what's going to happen is that the table.bucketIndex is going to update itself to the next. So this will become the new head of our linked list, essentially. This is not going to run. Previous is equal to current. And then this is going to run here. And so anytime string compare actually runs itself, it means that there was a match, essentially. And we need to... We're going to have to break out somewhere. Yeah. Yep. But where are we breaking out, though? I'm really not sure if I'm updating this correctly. I really think that this has to be... Let me cut this. Has to be outside here. Inside of this while. I really do think so. This makes the most sense to me. Right, and then when we're done here, right, once we found a match, essentially, then we'll say, we'll free, what do we need to free? Actually, there's two things we need to free. we need to free current.key, right? Because remember that's a pointer. And then we need to free current itself. Yeah. Free current itself, and then we can return. We can break out from here. Ah, yeah, that makes so much sense to me now. Of course, I could just be completely wrong on this implementation. It's just scuffed to the moon. So, yeah, so what's going to happen is that it's going to run this, right? This is not going to happen, and it's going to free the key, it's going to free current. This is gone now, and it's going to return us out. Now, there's the other case we will consider now, is that we want to remove not this node, but we want to remove something here, like Najdorf, right? Remember we did Apple and Najdorf when there was a collision. I don't remember which collided with which. I suppose it would depend on which one you put into the hash table first, right? So let's assume that what we wanted to, the node we wanted to delete was here instead, right? And so what's going to happen is that same thing, right? It's going to string compare. It's going to say, okay, well, current is not equal to null, and it's going to string compare. It's going to be at the first node here, and it's going to string compare, and it's going to say, okay, I didn't find a match for Najdorf, right? And so nothing here is going to run, right? It's going to come down here, and it's going to say previous is equal to current, right? And remember, current it's the starting node, so it's this one here. So previous is going to be this guy here, and then current would be current.next. So this is going to become current now, and then it's going to come up back at the top here, and it's going to string compare, and it's going to find a match, right? Because that's Najdorf. And it's going to say, okay, well, is previous equal to null? No, right? Because we've updated previous to be this now. And they say, oh, okay, well then previous.next, right, would be current.next. So we bypassed, like so. We bypassed. And then we free the key, free the node, and you break out of the structure, and then this is gone. Okay? And this is just now pointing to the next value. And remember, this doesn't have to be null. This could be literally a node, and there could be null after this, for instance. And so this will work in the general case as well, I think. So my sense tells me. All right, so the moment of truth. Let's see if we hit the nail on the head, or we're getting hit in the head instead. So delete table, and let's delete Apple. Yeah, let's delete Apple. There we go, Apple's gone. And actually, let me comment this out. Clear. So yeah, you can see that Najdorf came first, right? And then Apple came second. And so yeah, we were able, it's literally just as we discussed just now. And then, hang on, did I do a typo or what? Oh no, this is where we were searching for something. Okay, and then we can delete instead for Najdorf. It's supposed to be Najdorf, I think. Is it Najdorf or Najdorf? I can't remember. I haven't played chess in so long. Wow, I can't spell Najdorf, which is insane. I'm pretty sure it's Najdorf. Not Najdorf, it's Najdorf. Yeah, 100% sure it's this. So let's delete Najdorf, and it should leave us with Apple. Right? And then let's delete Apple out as well. Now let's delete Apple, and we should just see null. Yeah, there we go. And okay, so that's just about everything pertaining to hash tables. And I hope this tutorial was not too long-winded or too complicated. If there's anything you're not too clear about, you'd like for me to clarify for you, just feel free to do so in the comment section, or you can just shoot me a message. Perfectly fine as well. But yeah, I hope this tutorial just shows you how you have to sort of understand what these data structures are, and sometimes you have to feel your way around the dark. I suppose every single time I implement this hash table, it's gonna be slightly different every single time, but the underlying principles are just going to be the same thing, right? So you need a hash function, right? You need to be able to create a node, and you need to be able to insert that node into your hash table. You need to be able to search your hash table, and you need to be able to delete from your hash table. And how you go about doing that is obviously up to your sense and what makes, what makes sense to you then. And you can see from my little diagrams I was drawing that that's how I was able to reason out and find a solution. So yeah, hopefully you were able to learn something, and yeah, have a good one, man.